In section 10.9, we start to look at the conservation of angular momentum. Our objectives here are to explain the connection between rotational inertia and rotational velocity, and also be able to apply conservation of angular momentum to solve problems. So one was linear momentum conserved. Remember, we learned about linear momentum being equal to an mv, and we said that linear momentum would be conserved in a closed and isolated system, meaning that the mass wasn't changing and meaning that there weren't any external forces acting on the system, or no net external force. In rotation, we have a very similar conservation law. It's the conservation of angular momentum. So the total angular momentum of a system will also be conserved if the net external torque is equal to 0. So just like we couldn't have a net outside force to conserve our momentum, we can't have an external torque in order to conserve angular momentum. Now remember, we said that the sum of the external torques could be set equal to dl dt. Now if this was going to be equal to 0, then that would mean that the net torque is also going to be equal to 0. And it would mean that dl dt is equal to 0, which means that L, or angular momentum, is not going to change with time, which basically just says that it's conserved. So before, we looked only at rigid objects, but with this particular law, this is going to work whether the system is rigid or not. So you could apply the conservation of angular momentum really to nearly any type of system as long as there wasn't any net external torque. This means that we now have 3 conservation laws: the conservation of energy, the conservation of linear momentum, and the conservation of angular momentum. Now here's what this looks like in just some real-life scenarios. Remember, we said that angular momentum could be found with an I omega, or taking a moment of inertia and multiplying by an angular velocity. Now, if this is going to be a conserved quantity, that would mean that if the moment of inertia were to increase, in order to conserve L and keep that value the same, the angular velocity would have to decrease, so that the product of these two is still the same. Or, if angular momentum was again going to be conserved and the moment of inertia were to decrease, then by necessity, the rotational velocity would have to increase, so that again the product stays the same. Now, examples of this would be like when you stand on the rotating platform in class. When you hold the weights very far away from your body, you have a very high moment of inertia, and you're moving fairly slowly. But when you pull those weights in very close to the axis of rotation, that is going to decrease your moment of inertia by pulling those masses in very close to the axis. And that now is going to result in a higher angular velocity. You're going to be spinning faster when you pull the masses closer in. This can also be seen with ice skaters when you see them performing a routine and they start kind of spinning around the ice with maybe their arms spread out and maybe even a leg kind of sticking out. And then by the end of their routine, they hold all those things in really close so that arms and legs are all very close to the axis of rotation, meaning that they begin to spin much, much faster near the ends of those routines. Another example is in a supernova explosion. Now, these are explosions of stars, essentially, and these stars can start out very, very massive and very, very large, but in the explosion, they begin to compress and become a much smaller sphere with a much higher density, meaning that they are going to lower their moment of inertia by bringing all of that mass in very, very close to the axis of rotation, and ultimately then ending with a much faster spin rate, so they go through more revolutions per second. So let's take a look at an example where we are conserving angular momentum. In this example, we have a puck of mass m on a horizontal frictionless table that's connected to a string that passes through a small hole in the table. The puck is set into circular motion of radius capital R, where its speed is initially some v sub I. But the string now gets pulled, so a force is applied down here at the bottom of the string, pulling the puck into a new, smaller radius for its rotation, a lowercase r. And the question is, what is the new speed of the puck if it's brought into this tighter rotation? Now, here we can look at conserving angular momentum. So our initial angular momentum needs to equal the final. And one way that we could find angular momentum was with an mvr. Our initial angular momentum would be mvi times capital R, and our final angular momentum would be mvf times the new lowercase r. These two quantities have to be equal because, again, this would be a situation where angular momentum would be conserved. Notice that the m's would cancel out on either side, and if we solve for the new final velocity, we would get a VIR over lowercase r. Another question we could ask ourselves is whether or not the kinetic energy is conserved. Would the energy that you start with be equal to the energy that you end with in terms of that kinetic energy? What we could do to solve for this would be to set up a ratio of K sub F over K sub I. If kinetic energy was conserved, then this ratio should be equal to 1. If it's not equal to 1, then we would know that kinetic energy is not conserved. So let's set up the ratio. We have a 1/2 mvf squared over 1/2 mvi squared. The halves and the m's will simply cancel out. And we are now left with the final velocity squared, which would be a VIR over lowercase r, all of that now being squared, over a VI squared. Which means that when we simplify this expression, we find that because these two radii are different values, our kinetic energy is in fact not conserved. And we could even say that since capital R is larger than lowercase r, what this ratio gives us is showing us that there's actually an increase in the total kinetic energy. And that increase makes sense in this case because that increase in kinetic energy is coming from the work that was put into this system from the outside force pulling down on the string. Here's another interesting example. In this example, we have a star that undergoes a supernova explosion. The material that's left behind forms a sphere of radius 8 times 10 to the 6th meters, just after the explosion, with a rotational period of 15 hours. What often happens to these stars is that the remaining material actually collapses into what we would call a neutron star. These neutron stars are extremely dense, and this one in the example has a radius of only 8 kilometers, or 8 times 10 to the 3rd meters. And the question is, once this now condenses down into this very dense neutron star, what is the new rotational period of the neutron star? Well, we know that this is going to be an isolated system without any net outside torque. So our angular momentum in the beginning will be equal to our final angular momentum. Here, angular momentum may be easiest to calculate as an I omega. And this I value would best be represented by modeling the stars as a sphere. If you look on page 300 in your books, you'd find that a solid sphere would have a moment of inertia of 2/5 mr squared. Now on the flip side of this, or the final neutron star, again we still have 2/5 mr squared and this new omega value. Now at this point we haven't been given any information on an omega value for the speed that the star is rotating at. We weren't given that information, nor are we even looking for it. So it might be wisest to take our omega and rewrite it in terms of a rotational period. Again, the period that we have here was originally 15 hours to make one full revolution. Here we have some number of new hours to make one full revolution. Either way, a full revolution is always 2 pi radians, and it's taking some amount of time to make that full revolution, which again we call the period of that motion. We can now come back into our equation here with some simplifications, knowing that the 2/5 will cancel out on either side, the m's will cancel out on either side, and we now have our initial radius squared multiplied by 2 pi over the initial rotational speed, and this can be set equal to our final radius squared multiplied by the 2 pi over the new final period. Take a minute, pause the video, and see if you can solve for t sub f. Again, you're looking for what is the final rotational period of this motion. When you plug in the values for the initial radius of 8 points, or 8 times 10 to the 6th, squaring that, and putting it over the 15 hours, and then the final radius of 8 times 10 to the 3rd, squaring that, and putting that over this new period, you end up finding that the new rotational period of the neutron star actually takes only 1.5 times 10 to the negative 5th hours to complete one full rotation of the star. If we were to convert this, we would find that this would come out to be a mere 0.054 seconds for a full rotation of that star. Think about that in comparison to the planet Earth. We make one full rotation of this planet in the course of 24 hours. This star makes full rotations in literally fractions of a second.